Okay, I'm going to go ahead and do this again. As hopefully you went through the first session and said, wow, we have a problem. We don't have any audio on this recording, and you did not. Sorry for that. I'm going to go ahead and do a second attempt so that you actually have the audio. All right. So the very first thing that I want to talk about is just a little background here. We have several different interactions that we talk about in relation to X-ray. We have two specifically that are responsible for the creation of X-ray photons, and that is a characteristic interaction or a Brem's interaction. These interactions are projectile-electron interactions with the target material. Okay, so that interaction between the projectile electron and the target material can make one of three things. We could either have a Brem's X-ray photon being created, a characteristic X-ray photon being created, or heat being created in the form of infrared radiation. So, that being said, we know that the majority of the projectile electrons' interaction with the target material result in heat, because 99% of the interactions just create heat. So one of the biggest problems we have in the X-ray tube is dissipating that heat and getting rid of that heat so that we do not damage the X-ray tube itself. So only 1% of the interactions actually result in X-rays. So Brem's, one of the important things about that is Brem's is not energy dependent. So why is that important to us? Because it occurs across the entire energy emission spectrum. Okay, so always the majority, if not all, up to a certain energy level, will be Brem's X-ray photon. So it always forms an emission, a continuous emission spectrum. So Brem's, again, at any energy level, Brem's is occurring. What's important about characteristic is not always a part of the X-rays that are created in our beam. So characteristic, we have to have at least 69.5 energy projectile electron interacting with our target atom to have enough energy and not too much energy to eject an inner shell electron. Okay, so if we don't have that level of energy, we have no characteristic in our diagnostic tube, because our K-shell binding energy for tungsten is 69.5. So that's important for you to recognize there. So again, that happens at a discrete level because it is at a specific energy, that 69.5 or 70 kV. Okay, so when we have Brem's, what we have is we have that projectile electron coming in. If it doesn't come as close to the nucleus, doesn't have as much attraction to the nuclear force field, because again, we're talking about that negative entity. So if it's not highly attracted, it's going to give off a low energy X-ray photon. So this was not really attracted to the nucleus, so the difference between that incoming energy and the exiting energy of that projectile electron, very little difference. On this one, however, the incoming projectile electron is very affected by the nuclear force field, so it lets off a lot of energy, and so this would result in a high energy Brem's X-ray photon, and exiting this projectile electron would have very little energy. So if we want to think about it this way, we could say this incoming projectile electron had 90 keV energy. When it exited, it had 80 keV energy. So this BREMS X-ray photon would only have 10 keV energy. Okay, that's all the energy it has. Now this one, say it came in with that same 90 keV of energy, and it exited with 40 keV. Then the difference between that 90 and 40 is 50. So now I would have 50 keV energy X-ray photon. So this would be a high energy X-ray photon. Obviously we can have higher energy than that, but you get the idea there between the two. So, and again, BREMS can be the only X-rays that are being produced based on the whether we have enough energy to create characteristics. So here is just a comparison between the two. Just BREMS moving past the nucleus. Remember, it's all about nuclear attraction. So if it comes in close enough to the nucleus, then it's going to slow it down more significantly, and it will produce a higher energy X-ray photon. Whereas if it's just slightly attracted to the nucleus, then it will give off a low energy X-ray photon. And again, that X-ray photon is the difference between that projectile electron's incoming and exiting energy. So a characteristic we know is based on the energy of the projectile electron. So we will not have any characteristic if we don't have a projectile electron that has the same or slightly higher energy than the binding energy of the target atom. So for us with tungsten, it's K shell, and we're talking about 69.5 binding energy, so we need at least that energy to cause that interaction to occur. So anything below that energy level will produce no characteristic X-ray photons. And once we get above that level, only the projectile electrons that have that energy that's even or slightly higher is going to interact with that inner shell. Okay, so we have that incoming projectile electron. It hits the electron, knocks it out, so it's ionized the atom, and then it continues on. So we have a ejected electron, and we have the projectile electron. So then what has to happen is we have to have the cascade effect. We'll have electrons from other shells that will drop in to the void to fill that vacancy in that shell. So when we create characteristic X-rays, these characteristic X-rays can have different energies based on the binding energies of the different shells. So if an L shell dropped into the K shell, then that would be that K shell 69 minus the binding energy of the L shell of 12, and that would produce a 57 keV energy X-ray photon. If we drop down from the M shell, then that would result in a 66 keV X-ray photon, because it would be 69 minus the 3, which is the binding energy of the M shell. Next, if it was an N shell, we'd have 69 again for the K shell minus 1 for the N shell, so we'd have a 68 keV X-ray photon that was created. So just to help you understand a little more that the characteristic X-ray photons can have different energies, but none of them will be at that 69 because they are always one binding energy minus the other, but they can be different energies that are produced. So again, this is just another diagram and showing you, there's your K characteristic photon, and here's your L X-ray photon. The only one that is considered to be useful in diagnostic X-ray is the K characteristic X-ray photons, because again, those would have that the energies of between 57 keV and 68 keV. X-ray photons would all be down in the low double digits, so they'd be about, I think they're around 16, 17 or so, as energy levels down to about 12. So obviously nothing we want to see in diagnostic imaging. Okay, so again, those are the two interactions that occur between a projectile electron and the target atom within the tube. These two interactions are the ones that are responsible for producing X-ray photons. So now, once we leave the tube with an X-ray photon, now we'll talk about the different ways that the X-ray photon actually interacts with matter. So, and we know that matter can be the patient, it can be our barriers, it can be anything in the X-ray room, including us if we're in the X-ray room. So the first thing that we want to talk about is the interactions that are important to us within the diagnostic range. So within the diagnostic range, the two interactions that occur and that are important to us as far as dose and the creation of an image would be photoelectric absorption and Compton scatter. So first, photoelectric absorption happens generally with lower energy X-rays, generally in the range of 40 to 70 keV, and Compton occurs around 70 to 100 keV. So that's important to distinguish between those two. Now, one of the things that's important to recognize about photoelectric absorption is photoelectric absorption is very, very similar to characteristic, but photoelectric absorption is happening with an X-ray photons interaction with matter versus a projectile electrons interaction with a target atom. So one, we're creating an X-ray photon, and the other, we have the X-ray photon and it's interacting with electrons in matter, okay? So that's important for you to recognize there. So here, now instead of a projectile electron, I have incoming X-ray, okay? This incoming X-ray comes in, it will eject the electron. That is now called a photoelectron that gets ejected. All the energy of this X-ray is absorbed within this atom, okay? Now, it will put off secondary radiation because we have the cascade effect. So we have an L shell coming and filling in the K shell, an M shell filling in the L shell. So we're producing secondary radiation within the patient, it gets absorbed within the patient. Another outcome is having an augury electron. But you only have probably one or two books that talk to you about the auger. Just recognize that that is considered a byproduct as well. So here, I just did a little comparison between the two. So here we have the photoelectric, which is inner shell. Okay, this happens within the inner shells. So it's not specific, doesn't only have to happen with the K shell, but it's within inner shells. Compton is outer shell, okay? So that being said, here comes our X-ray photon. It's coming in. It's going to be eject the inner shell electron. It's going to be completely absorbed. So this is what's responsible for patient dose. So when we're talking about doing extremities and all, we know we rely on photoelectric effect, which is that absorption of that X-ray photon, because now that produces a minus density area because there are no X-ray photons left to interact with the imaging plate. So that's important for us to recognize there. So it's the absence of information that's actually useful to us, but that absence of information represents a bigger gain in patient dose. Okay, so it's not a good thing for the patient to have a lot of photoelectric effect. But again, knocking out that inner shell electron, absorbing all the X-ray photons energy, we have the cascade effect where we are creating secondary radiation that's going to be absorbed by the patient. The other interaction that we have is Compton, and again, this is outer shell, strictly outer shell. X-ray photon coming in, it ejects that outer shell electron, which could be considered a recoil electron, and then we have a scattered X-ray photon. So this again happening at a higher energy level. So when we talk about attenuation within a patient, that is that combination of absorption from photoelectric interactions and scattering from Compton interactions. Both of those help us reduce the number of X-ray photons as the X-rays travel through the patient. If an X-ray has enough energy to travel through a patient without interaction, that's considered transmission, and that X-ray would be a remnant X-ray, and that would interact with the IR. Okay, so now the last thing we have to talk about is those interactions that occur above and below the diagnostic X-ray range. So they're not really important to us other than in recognition. And if you go on to another modality, they could become important to you. But at this point, it's just to exclude answers or be able to say, nope, that's what they're describing. Or if they say it's occurring in the diagnostic range, then you know it's not any of these. So the very first thing we'll talk about is interactions that occur below the diagnostic range. And the only one you have that you have to know is coherent. And coherent occurs below 10 keV, so very, very low. That's why it's insignificant to us in diagnostic imaging. It is non-ionizing, which is very different than in photoelectric, which are both ionizing. And that means that they change the atom. They create an ionized atom. That's not a good thing because all the atoms have to reach stability before any damage that's occurring can stop occurring. So coherent, again, non-ionizing, it's just a vibration or excitation. We have the incoming X-ray photon, real low energy. It's going through, comes in one direction, and it leaves in a slightly different direction. Okay, that's what's happening there. So it's a vibration or an excitation to the atom, and that's it. So some of the things to recognize about coherent is it can be referred to as classical, it can be referred to as Thomson, Rayleigh, several different names that you would want to recognize. But again, non-ionizing, just a change in direction. So again, the energy level, that 10 keV, very low to us and not significant to us in the diagnostic range. Now, the next interactions are interactions that occur well above our energy range for diagnostic X-ray. So the first one we'll talk about is pair production. And in pair production, we have to have an energy of at least 1.02 MeV for this to occur. Okay, and so we're talking like linear accelerators, radiation therapy levels. This is considered an annihilation interaction, a matter, antimatter, and the byproducts are a positron and a negatron, or what can be referred to as a positively charged electron and an electron. The energy, incoming energy, is split equally between those two byproducts. So if we talked about it coming in, the X-ray photon coming in at 1.02 MeV, then the positron and negatron would each have 511 keV as their energy, or if you wanted it in MeV, it would be 0.51 MeV for each of them. Okay, and this is just showing you the interaction occurring. And here's another one and showing you your positron and negatron there. And the last interaction is even at a higher energy level, and that's photodisintegration. And photodisintegration has to have an energy of 10 MeV or above to occur. So this interaction, this X-ray interaction, is the X-ray interacting with the nucleus, and the nucleus ejects a nuclear fragment at the point of impact. So we have the X-ray coming in, collision with the nucleus, and a nuclear particle or fragment is ejected. It could be a proton, it could be a neutron, alpha, a nucleon, anything ejected there. So just I think they'll even tell you, yeah, nucleon, it could be a neutrino. Again, not within the diagnostic range. The photon actually interacts with the nucleus, and that nucleus ejects a nuclear particle so that it can regain stability. So it's trying to become stable again. All right, so those are all our interactions. So again, how do I tell all these interactions apart from one to another? For pair production, photodisintegration, and coherent, it's most important that we recognize that they do not occur within the diagnostic range, but that they are X-ray interactions with matter. What's important for us to recognize about photoelectric and Compton is, one, photoelectric is patient dose because it is the absorption of that X-ray photon, whereas Compton is responsible for our occupational dose because this is scattered X-ray. So this is what we use our cardinal principles to protect ourselves from: times distance and shielding. Most importantly, distance explained in the inverse square law. So those are all interactions with matter. So they already are outside the tube. Okay, that's the most important thing to recognize, is these are X-ray interactions with matter. Whereas when we talk about Brem's and characteristic, we are talking about the creation of the X-ray photon. And we can either have Brem's X-rays or characteristic X-rays, or we can have heat. All of those things are generated within the X-ray tube, and all of them are a result of a projectile electron's interaction with the target atom. Okay, well, I really hope that helped you and is a little pre-session for you before we come in tomorrow to discuss interactions, so that if you came up with questions from this information, you can bring them in tomorrow for our review and discussion. Thank you, guys. See you tomorrow.